So thank you, Aude. And I would really like to thank the organizers. I felt very honored when you invited me here, guys and ladies. So thank you, thank you. And this talk is dedicated to my advisor, Jos Heinz, who passed away 5 months ago. And this is, you heard about him because yesterday Francois mentioned him already with his meaty face and, no? This is not random. When I chose the subject, when I finally could choose the subject of this course, this is completely inspired by him. So I started to work on these subjects when we started to work together with Jos and the group he formed back in 1987. And I will start with something very, very linked with him. So I will, but let me first give you some disclaimers. This is about bounds. It's not about algorithms. There are algorithms, many algorithms behind what I'm going to say, but I won't speak about algorithms. I will only speak about bounds. The problems I will treat will always be defined over the rational numbers, or simpler, over the integer numbers, but we are speaking of classical algebraic geometry. So I will write the setting here, but my setting is polynomial equations that will generally be defined over the integer numbers, simplest possible representation. So my polynomials will be given in dense form. There are many other representations nowadays, a lot of people working on all these representations. Mine will be the simplest one, dense form, which means that the parameters measuring the polynomials will be the number of variables, the degree of the polynomials, and in the case of integer polynomials, what I will call the height. So the height is just the max binary size of each of the coefficients of a polynomial taken in absolute value. So that will be the size. It will be the log base 2 log of the absolute value of the coefficients, and you take the max. So these will be the parameters that will appear in all what I'm saying. So for simplicity, I will restrict to the zero-dimensional case. I will write what it is, and to the case when a variety defined by my system of equations is empty. So dimensions -1 and 0. There are so many extensions of what I'm going to describe here, many of them made by people in this room. So extensions instead of dimension 0, in positive dimension. Extensions in the representation. You can have, instead of having my dense, everything is affine. No projective here. Everything I will do is affine, and everything is without assuming genericity conditions. So I will never assume genericity conditions like, okay, my n polynomials cut well, and then after the n I have only a finite number of points, or transversal intersections, or this kind of assumptions that always appear often in the literature. Here, it's S polynomials in n variables and no conditions of how these S polynomials behave, except that my assumptions will be empty variety or zero-dimensional variety. I will write this, but I have one more disclaimer. So extensions. There are algorithms for what I am explaining without algorithms, not done by me, by people here and by people abroad. They are extensions for positive dimension. They are extensions to the projective, multi-projective, sparse, lacunary, and also with their encodings. Each of these other settings have their own encodings. Also, there is a lot of work done by Jos school from the beginning for the straight line program representation of the polynomials, which is another encoding of polynomials. And what else? Again, a lot of people here worked on that. So please, I am apologizing. I wrote some notes that I will make available when the course is finished. And I tried to cite people. I surely forgot a lot of people. I am already apologizing for that. And again, thank you very much for the invitation. So really, I'm very pleased. So let me write the setting. So my setting is that, okay, my setting is that I will have polynomials in n variables, and soon, instead of C, I will consider only integer polynomials with integer coefficients. So I will denote by V the variety defined by these polynomials, which means the set of common roots of all the polynomials in C to the n. Okay? And what else? I will only consider the situation when this variety is empty, so there are no common zeros. And as I think many of you know, and it will be one of the subjects of this talk, this is by the Nullstellensatz equivalent to the fact that the ideal generated by F1, Fs is the whole polynomial ring. So I will discuss this a little bit later. So ideal generated by means all polynomial combinations of these polynomials. Okay, so this is one of my conditions. And the other setting will be the case that we call dimension 0. So this, by definition, is that the variety defined by these by the polynomials. So I is the ideal generated by F1 Fs, which is included in C of x, 1xn, or Q of x1, xn if one takes polynomials with integer coefficients, so in the right setting. So this is by definition that the variety defined by the polynomials I is not empty. I separate, empty is another case, but finite. But not empty. And so only finite points in the variety, and this is equivalent to say that the quotient ring, let's say C of x over I, which is a vector space over the complex, has finite dimension. So this dimension is finite, but non-zero. So I will mostly concentrate into these two cases. Okay? Setting? So soon, as I said, I will consider polynomials with integer coefficients. And under this, well, let's start in general. And I will always say that the I is the degree of the polynomial fi. And I will call hi what I said, the height of the polynomial fi. And this is the max log of the absolute value of the coefficients of fi for any integer polynomial. So when fi is integer. So I will start by the Bézout bound. So I don't know here, no? So Bézout bound. Is everybody familiar with the Bézout bound? So we have a system of polynomial equations which define zero-dimensional, this is called zero-dimensional, which define a zero-dimensional variety, and then the...
You may want to put the black box.
Yes, you are right. So I didn't say something. The number of points in my variety is what we call the degree of the variety. That's the number of points. When it's not empty, let's say. So the number of points is the degree. That is the classical notion of geometric degree of a variety. And all this material can be found in this nice book by Cox Little-Oshie in the first chapters. You have all for this. So Bézout bound, one says, okay, if you have two polynomials in two variables, generically they have exactly the product of the degrees, number of roots. So this is in a projective setting. It's in general. It has all these things of genericity that I was mentioning before. But the one I will discuss a little bit now is what we call the Bézout inequality, and I will just discuss it a little bit in the way that Jos introduced it in his thesis. So that is the version that one can derive from Jos is Jos Heinz, from Jos' result in his thesis. So if you have any number of polynomials, one more thing I didn't say. In order for S polynomials to define a finite number of points, S has to be greater or equal to the number of variables. So because every time you add one polynomial, two things can happen. Or you kill everything and you stay with nothing, or for the components you have at some level, you cut the... So you have three possibilities, actually. So imagine that you have a variety like this, and you cut it with a polynomial. Three situations. Maybe you cut nothing and you stay with nothing somehow, or you cut it well and you reduce the dimension by 1, or this is included in this and you don't reduce anything. So if you want to arrive to a non-empty variety of dimension 0, you need at least n polynomials. So in this setting, S will always be greater than n. When people speak about generically or generic situation, they assume that S equal n, but it might be bigger.
In the inequality of degrees, you don't consider ds?
No, that's a nice thing, and that is, I will discuss that. Thank you for observing it. ds, so what the Bézout inequality says is that, it's nice. Usually ds will be the smaller one. The most interesting case is when ds is a smaller one. But what the Bézout inequality says is that if you order your polynomials, d1 greater than d2 greater than ds minus 1, and then one polynomial independent, you don't care about him, you know that the number of points, if the variety is finite, you know that the number of points is bounded by the products of the n minus 1 bigger ones and the other one. And this other one is usually taken to be the smallest one. So that's why I wrote n minus 1 ds. If all but one polynomials are bounded by degree d, and you have ds is the smallest one, you have this bound for the number of points. So let me show a couple of examples. This is an inequality. And how is this achieved, actually? Why is not this the product of all the polynomials? Here I am only taking n polynomials. But that is because, in general, if you have a variety, a finite variety defined by s polynomials, what you can do is, okay, you take one polynomial, the last one, fs. It defines a hypersurface. It may have many components, but it is a hypersurface. And then you can choose a linear combination of all the polynomials such that it really cuts every components of the hypersurface, well, so it reduces the dimension by 1. And then you can choose another linear combinations of all the polynomials, such that for each component you have a dimension n minus 2 because you cut well. So what I'm saying is that in the end, you take linear combinations. So I said, okay, you started with fs. You can always do that. And then you take a linear combination of all the polynomials. Let's call it a2s fs plus a21 f1 plus a2 s minus 1 fs minus 1. And here you reduce your dimension by 1. And then you keep going. But if at every step you reduce your dimension by 1, after n steps, you will be reducing your dimension by n. You will be in the 0-dimensional case. So here, you will have a 0-dimensional variety. And the zeros of your original variety are contained in this, because this ideal is contained in your original ideal. So if you have a 0 of fs, f1, fs minus 1, you will have a 0 of this. And this has a finite number of points. So your original variety is included in this one. But once we have this system, you can triangularize it. Because with this one, you can just get rid of this. So here you have degree fs. Here you will have the max of the following degrees. And then once you have this maximum, you can keep triangularizing, and then you will obtain a triangular situation. So I don't know if it's n or n minus 1, but this will disappear. So this is an explanation which says that the number of solutions, the number of roots, of common roots, is bounded by the degree of, using the classical Bézout inequality. For n polynomials, it's bounded by the degree of fs, degree of f1, degree of fn minus 1, something like that. This is also found in some material written by Jos, and I will, the references are in the text. So anyway, let me give some examples. Yes, sorry, Bernard. Yes, but I'm not speaking about multiplicities in this course. Yes, it is true with multiplicities, but I won't speak about multiplicities. My varieties are just geometric varieties, not schemes and not, Yes, you are right. Couple of examples. If I take these polynomials, how many zeros do they have? In C to the n. D to the n, right? Well, each coordinate is a root of unity. So this has d to the n. So the degree, this is v1. The degree of v1 is d to the n, which agrees with the Bézout bound, in this case, d to the n, because each polynomial has degree d. But what about this, this one? So I write 2 to the h because this is the classical number which height is log of 2 to the h. So this is log. No, I have to write something. What happened in this case? So x1 is 2 to the h. x2 is 2 to the h to the d, 2 to the dh. To the, I will spare you the, so this is the only point in this variety. So in this case, the Bézout inequality is really strict. So it's only, there is only one point in the variety, and here the Bézout bound would be 1 times d to the n minus 1, okay? So anyway, this was to introduce, this example is not random, it was to introduce that we have an arithmetic version of this Bézout inequality. And the arithmetic version we have of this Bézout inequality is based on the notion of height of a variety. So the height of the notion of height of a variety that I will use here is a notion introduced by Patrice Philippon from Paris in '95. This is the third of of a series of papers by him. This is not the most sophisticated notion of height, but it is really very useful, and it is very close to the other notions of height that exist and that are more sophisticated. So what he does, actually, given, and I will only introduce it in the case of finite varieties, non-empty finite varieties. So you have a finite variety. My finite variety are these points zeta, and then I take these variables and look at what I wrote there. What I wrote there is a linear form with coefficients, the coordinates of one of these points. So what does that mean? That means that if I specialize u0, u1, un into values, if I look at this as at an equation, no, let me tell it differently. Imagine that this is an equation. This is a linear equation. When does it vanish? When this linear equation in u0, un, when does it vanish? I have my point here. When does this linear equation vanish? When I have an hyperplane which passes through the point. Good? Okay, but normally, if I have a point, almost any hyperplane won't meet that point. There are so many hyperplanes, they won't meet that point. So this characterizes the hyperplanes that meet that point. So what happens if I take this polynomial? This polynomial is the product of over all the zeros of hyperplanes that meet each point. So that is a polynomial in u0, un. It happens to be homogeneous. It has degree d. It has a degree of the number of points we have. I will call that capital D. And it happens if my variety is defined over the rational numbers, this polynomial, which should be in C of u, happens to be in Q of u, because the variety is defined over the rational numbers. So this polynomial is a polynomial. What is its feature? Its feature is that this is a polynomial which detects when a hyperplane meets one of the points of my variety. So normally, if you have a finite number of points, almost any choice of hyperplanes won't meet any point. So these are very special. This defines the hyperplanes which meet one of the points of my variety. And this is, if I properly multiply it by a common denominator, because it's in the Q of u, so I can take a common denominator. I can, the smallest one, I can multiply by it, and this will be now a polynomial in Z of u. which is, I can choose it primitive. So there are no GCD between the coefficients. See, this is what I will call the Chow form of U. So the Chow form of U, the primitive Chow form of U, is a polynomial in Z of U, which characterizes when the hyperplane meets the variety. Okay? And Philippon defined the height of the variety through this polynomial using, yes?
I'm disturbed by, are you assuming that the roots in V are all living in Q?
No, no, not at all. Not at all. Not at all.
If you have a zero which is in C, how I'm missing something.
Yes, you are missing the fact. You're missing the fact that the variety is defined over Q. Each root individually are in C, but they have, imagine you have only one polynomial.
When you multiply all of them, it lies in, okay, each linear.
Exactly, each linear is in C, but when you multiply all of them, they lie in Q. It's the same situation as in with one variable, okay?
Teresa?
Yes.
I don't get that U passes at points of V first because
You don't get what?
at points of V. You say it passes at points of V.
If
The number of variables is not the same.
No. When you specialize the use, when is this 0? Okay. For which use is this 0? Imagine this is 0.
Dot, 1 and 0, for example.
Imagine you have a U0 to UN, which is a 0 of that. Okay? So that means that one of these terms is 0. Okay? So one of these, the term U0 plus zeta 1 U1 plus zeta n UN will be 0, which means that the hyperplane U0 plus U1 x1 plus UN xn will pass through the point zeta. You have an interplay of roles here. So anyway, Philippon defined the height of his zero-dimensional variety through this Chow form. It's related to the height of the Chow form. Actually, it's not exactly the Chow of the height form. His definition is a little bit more subtle. It's a kind of Mahler measure of this polynomial. I won't introduce that, but the fact is that the height of the variety V, which is defined through a Mahler measure of this Chow form, satisfies two things. In some way, it measures the size of the points in my variety. So these points in my variety, here, that's not what I was here, oh, flower. These points here do not have integer or rational coordinates. They are, so I'm not speaking of height here, I'm speaking of the log of the two norms. This one here is very nice because this means that nothing here is less than 1, than 0. Nothing is negative here because I have this 1. So this is 1 plus zeta 1 square plus zeta n square, square root of. This is actually greater than any absolute value of any coordinate. No, the coordinate zeta I in absolute value is bounded by this quantity. So that's good thing is that the height of the variety controls the size of the sum of the sizes of all the points in the variety. And the other things is, okay, this is a kind of difficult definition because it uses a suitable integral using Chow V, but there is a relation between the height of the variety and the height of the polynomial that I can measure because this is an integer polynomial. So this relation will also be helpful.
I just missed the definition. The height of V is the maximum?
No. The height of V is the thing I didn't define. I hide it. Because it's an integral, it's a Mahler measure of this polynomial. So it's taking some kind of integral of this polynomial in Sn. So that I'm hiding it. So anyway, with this in our hands, we have work, maybe there, maybe there, maybe there. Je peux faire ça ici. Here, we have this arithmetic Bézout inequality. Again, no genericities at all. So we have S polynomials that define a zero-dimensional, that are a zero-dimensional ideal, zero-dimensional variety, finite number of points. Here, all polynomials are in Z of X, and all of them have their degree and have their height, their own height. And I order the polynomials in order, but not all of them. One of the polynomials, I can choose it as I wish. So I will have one distinguished polynomial with its own degree and own height, and then all the others are like, you know, all together. So I order them from max degree to min degree, but they will all have a height bounded by the same quantity. So in this statement, I can only distinguish one polynomial with its height, and all the others will have the height, a common height, bounded by a common number h. So what Bézout, this arithmetic Bézout inequality says is that the height of the variety is bounded by exactly this quantity. So another thing I want to say is I'm never using the notation O of or O tilde of, because I want to show that the constants we obtain are neat, are very neat. So in this case, we have this constant n minus 1 here and 2n log n plus 1 here. So the height of the variety V is bounded by this quantity, which is kind of hard to read, so I prefer the second line. So the second line says, okay, this is my distinguished polynomial, fs, which has height hs, and hs appeared multiplied by d to the n minus 1. Then all the others have this behavior here. Everything which says h is related to heights, and then there is this kind of term which only contains degrees. And remember that this was an upper bound for the behavior of all the roots in my variety. It was the sum of the logs of all the roots. So I recall it. Ça marche plus, ce truc. I recall it here. Remember, we had this. And so in particular, c'est moi qui l'ai fait. So in particular, for any coordinate here, for any zeta, for any root, any of its coordinates is bounded by this quantity. Okay? And this bound, so let's look here in my examples. In my examples here, V1, what is the height of the roots? What is not the height of the roots? What is this, this log, oops, sorry, now it works. So what is this log zeta I here? Zeta I, all zeta i's has absolute value 1. So when I take the log, it's 0. So in this example, what it says is that, let's look at it here. So the sum of all the log of all the coordinates is bounded by the height of the variety. So every one of these, every coordinate has height 0, but they are d to the n of them. So what does this give? What is the height of this polynomial, x1d minus 1? 0. All of these here have height 0. So there are no heights in this here. No height, no height, no heights. And it just says that the log of the psi i's is bounded by 2n log n plus 1 d to the n, while there are d to the n points. So so there is some kind of garbage here, but it's not too big. But look at in this case, second case, we have only one point, and the point which is its height. The last coordinate of this point has height d to the n minus 1 times h. And what does this say? This say, okay, hs is hs. This will be my hs. What is the height of this polynomial? H. And all other polynomials have height 0. So I will have d to the n minus 1 h plus 0, everything here disappears, plus this quantity. I cannot get rid of this quantity. It belongs to the, we cannot get rid of that. So anyway, we have that the height of the last coordinate of this point is d to the n minus 1 h, while the theorem would give d to the n minus 1 h plus this quantity depending on the degrees. Okay? So in some way, this is what I wanted to say about. Can you see if I write here? Because I'd like to keep the statement. Because this has consequences. Once we have the height of all coordinates, we can evaluate any polynomial p in C of x1, xn. We can evaluate it in any root of this variety. And we can compute this quantity. So we have, once we have that, we can derive bounds, upper bounds, for the logs of any polynomial evaluated in the roots of my variety. And the bounds we will obtain will depend on this. Okay, because this polynomial will have its own height, its own degree, and we just make the computation. But more interestingly, and I don't know if I have it here, let me see. No, that's before. But more interestingly, what is I think more interesting is that you can also imagine that you have a polynomial which evaluated on a root is not 0. Then you can give a lower bound for a lower bound for the height you obtain, but only for polynomials in Z of x1, xn. Look what I do. Instead of considering the ideal f1fs, the original ideal f1fs, I have a polynomial p, and I want to know how does p of psi behave for any psi in this variety. So I will evaluate, I will add a polynomial, where I am, I'm lost, sorry. Sorry for that. Because here. So these are polynomials in X, and I add a new variable, and I add. So my first polynomials are all in X, x1, xn, and then I add a new variable. So this is now an ideal. Imagine that P is in Z of X, and it has its own degree and its own height, this polynomial P. So when I do that, I am now in Q of X, xn plus 1, right? And who are the zeros of this ideal? The zeros of this ideal are the original zeros, and also you have to have a 0 here. So which means that the zeros are the original zeta and 1 minus x plus n p of zeta. If p of zeta is not 0, that means that it's 1 over p of zeta, right? These are the zeros. But my previous result says how large can be the height of all these coordinates. So using that, I have an upper bound for the log of 1 over p of zeta. Yeah? So I have a lower bound for the log of, negative lower bound for the log of p of zeta. But this shows that when a variety is defined over the rationals, the roots cannot be as close as 0 as they want to be. They are 0, or there is some kind of distance. Not only that, because of this theorem, we can only have bounds for the separations of the roots that generalize the bounds that appear in this beautiful book by Maurice Mignot. So when he has a book called Mathématiques pour le calcul formel. So I think it's 1979, and it has a lot of material, but in particular, it shows it's univariate polynomials, but he shows upper bounds, and when the polynomials are defined over Z, he also shows lower bounds for the roots that are not 0, depending on the coefficients of the polynomial. So here we can do exactly the same. We can derive bounds for the separation of the roots. This only makes sense when my variety is defined over the rationals, integers. This won't make sense if we define a variety over the complex numbers, because we can get as close to 0 as we want. And for the separations of the root, what we have to do is duplicate this ideal. So let me try to find where I am. Let's look at inequality. It's horrible when one doesn't see. So if you take now as the ideal J, you take f1 of x, fs of x, and then you add more variables, y's. Okay? So this variety is also finite, because it's a Cartesian product, somehow it's finite, and I will add one polynomial, which is p of x minus p of y. So now I have an ideal. Look, the number of polynomial there is no generic assumption here at all. And then what are the roots here?
Intersection of the...
So it's a diagonal somehow, no? P of x has to be equal to P of y. So when I can have upper bounds and lower bounds for the roots of this variety in terms of the original parameters. The only thing I did is to duplicate the number of variables. And when I do that, I obtain the root separation, because I have lower bounds for these two. So I can obtain root separations. Yes?
So, in the case of a triangular system like you showed, it seems like, depending on the degree of x2 that you do, for instance, either you will multiply the height by something, or you will multiply the degree.
Here?
Yeah. So my question is, can we hope for an inequality like this where you put degree times height on the left?
Excuse me?
Can you hope for an inequality like this where you put degree times height on the left? Like it seems you have in the
there,
Yeah.
degree time height without.
I mean, I don't know what would be on the right, but in the two triangular examples, you have either degree, the degree is close to the inequality, or the height is close to the inequality, but not both.
So actually, there is some kind of trade-off, no? Number of roots and height of the roots. Unfortunately, so in our first example, this degree term took care of the number of roots. Unfortunately, the methods we know until now do not allow us to get an expression without a sum. And this is due to a stupid reason, but it's due because, for instance, if you do all the same thing, but instead of starting with z, you start with as parameters, instead of starting with integers, you start with polynomials in some parameters t1, tm, things behave way better. You will not have this junk term in the end. And the reason is that when you have polynomials, the degree of the product is the sum of the degrees, and the degree of the sum is the max. But the equivalent for integers is taking log. The log of the product is the sum, that's okay. But the log of the sum is not the max. It's a max plus something. And this plus something is the garbage that always appears here, and we cannot get rid of that. So until now, the methods won't help getting rid of this. And also, you will have to get a formula which balance number and height. But I don't know how to do it.
Your question, you want to replace this product? You want the end? Yes.
No, it's not about the right term. It's about, and like it seems like in the two examples, either you have degree d to the n and height 1, or you have degree 1 and height.
But one can produce more examples. These are very chosen examples to show the very specific cases.
I think already in the univariate case you will see the term appear. If in univariate case you have examples where you can do x plus 1 power n d, for instance, something like that, you know.
Yes, and what I would like to say again.
Maybe one more question. In the case where the zeta have rational coordinates, I would expect the arithmetic Bézout inequality to give me bounds on both numerator and denominator. But if I have only a bound on the absolute value of the rational number, I don't have this separate bound on the numerator and denominator.
Yes, it appears. It appears because take 2x minus 1, for instance, and make the computation, and you will see it appears because of this the definition of the height of the variety and the relationship. So the height of the variety is not exactly the height of the Chow form. There is a term, and this term takes care of the denominators. So yes, it is. So anyway, what I wanted to show, but maybe in the end here I got a little bit messy, but I wanted to show that this theorem, well applied, also gives bounds for the separations of the roots. So it gives bounds for P of z minus P of xi. If z and xi are two different roots, it gives bounds for the separations of the roots. And these bounds, again, essentially agree with the bounds that are that appear in the literature. In particular, there are bounds by Kani, by Yap, by a paper by Bernard and Ioannis and Elias. And they even give an example of a multivariate system of equations, which is based on Mignot's example of integer polynomial with two roots that are quite close. So they even give an example of that where they show a lower bound. They show an example where the roots are very, very close, and the bounds we obtain here are quite close to the example, to the roots obtained, to the distance obtained by the roots they showed. But it's quite a sophisticated example. I'm not going to introduce it here. The references are in the note. So this is about, sorry.
On the previous slide,
Yeah.
the term depending on the degree was, I believe, 3n plus 1 at the degree. And now it's 2n log n plus, 3 log n plus 1 times the degree.
On the previous slide, but because it's not exactly the same that I here.
Yeah.
But I didn't use that yet. I only used the first one. I never used the second yet. So this one is for tomorrow. So anyway, what I wanted to show you is that this kind of bounds can help having bounds for the roots, bounds for the evaluation of a polynomial on the roots, and bounds for the separations of the roots, and all this. Now I'm going to switch to, that is not what I wanted to show, this. I want to switch to another subject. So, finish with the past? This is the other, yeah, sorry.
Why did you mentioned there was you would fail for non-rational numbers, complex numbers? So,
because if you have an upper bound for the...
What was the question? I'm sorry.
Why does this fail if I take polynomials defined over the complex numbers? Because if I only take an upper bound for the coefficients, you can have the polynomial x minus 1 over epsilon. Or, I don't know, epsilon x plus 1 or something like that. So how do you measure the coefficients?
At least you can do it for a fixed number of fields instead of cubes.
Yes. All these works on number fields. There is a notion of height for number fields, so everything extends to number fields, yeah.
Another question. So how of curiosity, in these proofs, are you really using the fact that your points are affine, or all these bounds would be the same if you are taking into account projective points?
The same.
The same.
Actually, all this is based on projective, yeah. But usually projective is kind of easier than affine.
Yeah.
So that's.
If you could rely somewhere, assuming that.
So that the fact that in our bounds, look here, this one that appears here as first coordinate is because you are using projective.
Okay. Thank you.
I was just wondering if you consider non-absolute median valuation, is it easier somehow? For example, p-adic valuation?
Okay, when we derived this, we considered local heights. So all this is done using local definition of local heights of varieties. So if you have a variety defined over Q, you have the ordinary absolute value coming from R, and then you have the local absolute values coming from the prime numbers. So we had to do something like that for each of absolute values, and then put everything together. So yes, it's done. But the notion of Chow form that I gave is kind of, it's simple because we are in the global case. If not, the normalized Chow form wouldn't be this one. You have to take another one. But it is, if you want, I can show it to you after. Nullstellensatz. Nullstellensatz. One of the most beautiful theorems in algebraic geometry, at least for me. I don't know if you agree. So it's kind of the key ingredient in algebraic geometry, used in so many ways. What does it say? If we have an ideal I in C of X, the Nullstellensatz, everybody knows it? So good, I just remind quickly the two forms. Weak Nullstellensatz says that the variety is empty if and only if the ideal is everything, is the whole ring, which is the same as saying that one belongs to the variety. Strong Nullstellensatz says that the polynomial vanishing on the roots of the ideal are exactly the radical of the ideal. Okay? So both forms, one is weak, one is strong, they are the same, they are equivalent. So I guess that everybody knows that going from the strong to the weak is easy, because if the variety is empty, then I is everything. Another thing that I think that everybody can note is that going from the right to the left is easy, because if the one belongs to the ideal, you cannot have a common root, because it should vanish one, and one doesn't vanish. So right to left is easy. Here also, right to left is easy, because the zeros of the radical defined here, everybody knows what the radical is. Polynomial to some power belong to the ideal. So if the zeros of the radical are the same than the zeros of the ideal, so if something vanishes, is here, it vanishes everywhere on all the zeros of I. The difficult direction is left to right. And what is usually done is that one goes from the weak Nullstellensatz to the strong Nullstellensatz using the famous Rabinowitz trick. So that's a very beautiful trick that allows to go from weak to strong. And there are many different proofs of this. Some of them are more sophisticated, some of them are more elementary. But for instance, there is a very simple proof based on resultants. I named resultants in the books by Cox, Little, and Oshie. But the first proofs go through some equivalent property based on the Zariski lemma. And what they show is how are the maximal ideals of C of x1, xn. And it's equivalent to characterize the maximal ideals in C of x1, xn. So this is about Nullstellensatz.
Slightly confusing because they are using I for two different things.
Okay, but yes, it's this I is not the ideal. It's what is the this I is the set of all polynomials that vanish on a set. But it's kind of it's usual to say I of x. I don't know. I should have put J. Sorry for that. Okay. So this statement, as it is, it's an existential statement. It's not effective. In which sense? Okay, now I know. I want to check if my variety is empty. Just let's check if one is in the ideal. How do you do that? So of course, Gröbner bases. Great. But Gröbner bases are not very good. If you, in the sense, are good for some things, but not for everything. If you start with polynomials with many variables, the chance is that your Gröbner basis computation may never end. So, okay. So people were looking for quantitative effective versions of this. What does that mean? Okay, if I know that one belongs to the ideal, can I say that 1 equals G1 F1 plus GS Fs with some prescribed degrees for the G1 GS? So that is what is called effective Nullstellensatz, putting bounds on the degrees. So now I'm going to use this. So having the bounds for F1, Fs, how can I say if there is such an expression, how there will be such an expression with degree of GIs bounded by which quantity? So the first person doing that was a student of Emmy Noether, Grete Hermann. She used resultants twice. She used resultants and she gave a proof that shows that if the polynomials fi have degree d, the bound was doubly exponential in the number of variables. So the bound for the degrees of the GI was of type d to the 2 to the n. Hopeless. And then there was a search and a series of results. The first result was Brown-Abel. So Brown-Abel achieved a bound of this type, if I'm not wrong. And then people working on that. And Jos, my advisor, again, he worked on that. And he got a simply exponential bound. And then there was this result by Collard, who gave the best bound of order d to the n, except if d, all the d's equal 2. That was kind of the search. And then Jelonek in, I think, 2006, gave the most beautiful proof because it uses the geometry of the problem somehow. So if I have time tomorrow, I will discuss that a little bit. But this is about degrees. But if you start with polynomials that are all in Q in Z of X, so they have all integer polynomials, the polynomial GIs that you can eventually obtain using linear algebra will have coefficients in Q of X. So if you start with polynomials, integer polynomials, the GIs, if they exist, will have coefficients in Q, which means that you can take a common denominator, and if you take a common denominator, you will get an expression like this, where A is a non-zero natural number. For me, natural numbers are non-zero, but I know that in France, 0 is in the natural, so non-zero. And everything here will be in Z of X. So it makes sense to ask, okay, if I start with F1, Fs of degree bounded by D and of height bounded by H, what is the worst height I can expect to obtain for A, G1, GS, height and degree at the same time, okay? That is what I call the arithmetic Nullstellensatz. Arithmetic Nullstellensatz. So this is the situation I was describing. Everything is in Z of X, the variety is empty. You have the degrees of the DJs, of the FJs, the heights of the FJ, and again, I am allowed to leave one polynomial aside. So all but one polynomial will be considered in block, but one, I can distinguish it, because it can be helpful for applications. So what the arithmetic Nullstellensatz says that I will, if the variety is empty, I will have an expression A equal G1 F1 plus GS Fs with degree bounds that are related to the best bounds obtained by people before, Collard and Jelonek, and these heights bound for the denominator A, the constant A, and the sum of the heights of the polynomial GIs plus Fi. So, and this is, I again, I could have put, say, C of n, a constant depending of n, but I want to show that this is a bad constant, but it is a constant. 15, it can be better, but I just looked at the constant. And here, the typical situation in this case, the typical situation when you have an empty variety is that you have n plus 1 polynomials. So in the situation of n plus 1 polynomials instead of s, this term here, which depends on s, will disappear. So this is the effective Nullstellensatz, arithmetic Nullstellensatz. And once again, I would like to convince you that these bounds are quite sharp. So we cannot expect really better than this. And let me give a little example. Nullstellensatz. So my example is the same than this one, but I will add a polynomial to make it so that it doesn't have common roots. So here it's forced. Xn has to be 0. But if xn has to be 0, xn minus 1 has to be 0. And then I have x2 has to be 0. And x1 has to be 0, but x1 is 2 to the h. So this variety is obviously empty. And I would like to see if I can say something about the degree and the height of a Bézout expression for that. So I know that I will have something like A equal G1 F1 plus Gn minus 1 Fn minus 1. I know that I will have an expression like that. And what happens? So look at what happens if I plug into this here, in this expression, I plug 2 to the h. I do the same that I did before, 2 to the dh, etc., etc. So I will have G1, 2 to the h, 2 to the dn minus 1 h, f1, etc., until the last one. So all the first disappears, and the only thing which is left is A equal Gn plus 1 times this zeta times 2 to the n minus 1 h to the d. Mm-hmm. Why zeta?
You get about it in Gn plus 1 where?
In zeta.
Yeah, what is
Zeta is the root.
Is there another root?
Where zeta is the root. No, zeta is this point.
Okay.
Zeta is this point. Okay, now we have to look at this firmly, but I don't know what I'm doing now. Sorry, I want to figure out why now A has to be at least this.
Gn plus 1 is an integer polynomial, right?
Yes.
Which takes integer values.
zeta, yes, this is integer. Everything is integer. So everything is integer. So this number divides this A. So this is, okay. And there is another classical result, classical example by Masser and Philippon, which show that the degree bound is also sharp. So we cannot expect any better degree bound than d to the n. So these bounds are again sharp. Okay, so, and I think I wrote that result on the notes, but now I'm not finding it, but I'm finding my pages. 9. Okay, so now I will turn to another subject, which I think many of you all know, and some of you maybe don't know. It's a subject that was already mentioned in the talks yesterday. It's about the shape lemma.
Excuse me, can you tell us a bit about how the proof of this works? Can you reduce it to what you have shown before?
So the proof of this is not exactly reducible to what I did before. It's kind of two different ways of thinking. It's not the same arguments. This is based off the notion of eliminance and resultance that was developed by Raymond, a student of Philippon. So he developed a theory of resultant, no, let me say. The proof of this exactly follows the proof by Jelonek for the effective Nullstellensatz for the degrees. What it does, it adds the arithmetics. It adds to Jelonek's proof. If I have time, I will discuss it a little bit tomorrow. But it does the arithmetics for Jelonek's proof. And all the arithmetical part is based on the work by Raymond. So we just developed what we needed based on the work by Raymond to get the arithmetics. So what Jelonek did is that he could find a Bézout expression for 1 equal J1 F1 plus GS Fs for the Nullstellensatz as a coefficient of a given algebraic equation that involves the original polynomials F1, Fs. So he could define a map, and when he looked at the the intrinsic equation of this map, of the image of the map, the intrinsic equation of the image of the map has one coefficient which gives a Nullstellensatz. So that is what is behind this proof. So, and maybe if I have time, I will discuss it a little bit tomorrow. It's very interesting, very nice proof. And it's kind of, he found the natural proof because all the previous proofs were very complicated. In fact, when I showed the arithmetic Bézout inequality, in the same paper we also had a version of the Nullstellensatz which was less precise than this one. And this previous proof was based on recurrence, on divisions. So you started dividing the last one by the last polynomial in a bigger algebra, in a quotient algebra, and then you kept adding polynomials. But the proof by Jelonek is not at all recursive. It's kind of, did I answer? Everybody? Okay. So I would like to speak a little bit about the shape lemma. I won't give the details today because it's already 1:15. No, 10:15. But what is interesting with the shape lemma says or shows that if you have an ideal which is zero-dimensional, that is, that it defines only a finite number of points, this ideal essentially is a univariate ideal, works as univariate ideal. And that is very interesting because for univariate polynomials, we have a lot more tools than for multivariate polynomials. For univariate polynomials, you have Euclidean division, and it helps a lot. While for multivariate polynomials, we all know that there are lots of problems. We need Gruber basis to imitate somehow the Euclidean division. So look at this. I'm going to draw a very small situation. Imagine that I have a variety defined by polynomials, and there are these 4 zeros. So, and I am so lucky that when I project these zeros on the first axis, they all have different images. And imagine, in addition, that my ideal is radical. So my ideal is really very good, it's radical, which means that it doesn't have multiple roots. All roots are... When an ideal is radical, when the ideal is radical, I am still in C now, what is good is that the dimension of this quotient ring is exactly the number of points of the variety. So these two notions coincide when the ideal is radical. So imagine we are in this situation. So of course, there is a polynomial. How many projections do I have? D. D is the number of roots. So I have D projections, and there is, of course, a polynomial of degree D in one variable which vanishes in all these roots. Okay? The polynomial is x1 minus this one, x1 minus this one, times x1. So there is a polynomial of degree D, which I can call like this, of degree D, which vanishes here. So it vanishes on all the zeros of my ideal. Nullstellensatz, fantastic. That means that the polynomial belongs to the radical of my ideal, but my ideal was radical. So this polynomial belongs to the ideal. Okay? So I found a univariate polynomial in the ideal. What about the other coordinates? What about the other things? Okay, which is the polynomial in x2 which on this point takes this value? So there is a polynomial which on this point takes this value. On this point takes this value. On this point takes this value, and on this point takes again the same value. So this is Lagrange interpolation. I can define a polynomial which takes good values. So this will express my variable x2 in terms of x1. Every time x1 is one of the roots here, x2 takes the value it has to take. And since we are in a radical situation, how many points do I have here? I have d points. And since we are in a radical situation, we have d points. I define d points. This is included in I undefined d points. They are the same ideal. So what I'm saying is that this is a very mock example in two variables, but that what I'm saying is that my ideal I is in fact the ideal generated by W0, omega 0 in one variable, and then all the other coordinates are expressed by that variable. This is shape lemma. This is a shape lemma. Shape lemma was already introduced by Kronecker before the 90s. And this shape lemma, of course, you will say, okay, but what happens if we are not in the lucky case that all coordinates here, all projections here are different? Okay, choose another direction. Oh no, but you are not lucky at all. For any coordinate, the projections are not injective. Okay, if you are in this situation, unlucky situation, like this, so you cannot choose any of the coordinates to project, there will always be a linear choice such that all projections are different. And then you will use this linear form to do the shape lemma. So, but this is the important fact here. So when you are in a zero-dimensional situation, everything is as if it were univariate, using the shape lemma. So the shape lemma is very much used in computer algebra. It was brought back to this by many, many authors, and many authors in the room too. And what I will do tomorrow is to give a statement, an effective statement for the shape lemma. So bounding, if I start with polynomials in z of x, which define a zero-dimensional variety, all the ingredients appearing in the shape lemma will be integer polynomials, and I will be interested in bounding not only the degrees, but the degrees is easy because it depends on the degrees here, and the heights. And this is what I will show tomorrow. I don't want to start because I wouldn't be able to do it in 5 minutes, but this is based on the work we did with Bernard last year and Lorenzo Baldi, and it is our version, but many people worked on that, so here too. So I don't want to, and it's very classical nowadays, except for maybe the height part, which is more original, okay? So I think we can just finish now and open it for questions.
So we had already a lot of questions, but do you have any other question?
You mentioned about generalization for sparse, or I don't know, with polytopes, and but you mentioned there are generalization of effective Nullstellensatz for sparse polynomial, or at least for convex representation, and there are also results for lacunary polynomial?
No, none that I know.
Okay.
No, because the problem with lacunary is that every time you do change of linear combination of, you destroy everything.
Which was,
So it's more difficult.
Yeah, okay. Thank you.
Thank you very much for your talk. I was just wondering if there are some connections with tropical geometry, because somehow these bounds, they are related to the log of the norm of the solutions of the variety, it seems, or maybe
I think there are extensions in tropical geometry, and Martin Sombra is doing some of that.
Okay.
That's we have to check his latest papers. So the paper I sent you does that, or something like that. That's it's maybe 2018 or something like that. I will check. Yeah, yeah.
Okay, thank you.
Thank you very much for the nice presentation. I have a question. Do you know how pessimistic are your bounds when we compare with the ones we know for univariate, for example? Because they have too many terms, but if we have only one polynomial and it's univariate, can we expect to use this method? It's better maybe to use I don't know, how it compares to Cauchy bound, or we should do the math and compare.
Yes. Also, in many of these proofs, you assume that n is greater than 1. strictly greater than 1, and you do the one case part because you have everything. So univariate word is magic. Everything happens. Everything is good. You have GCD. You have you have Euclidean. So, but here we don't. Here actually my bounds are bad because of the n = 1 situation. So because I don't want to make a difference between one and others.
So you can improve them if you discriminate these cases?
Yes, you can improve if you... yes.
Thank you.
Pierre, Jean.
Another question.
I was just wondering if there are some dependency in the constant in the bounds with respect to the basis of the logarithm that you choose. For instance,
No, actually, yes, I chose 2, but you will see that every time in the left and in the right, you have the same logarithms. So there is no difference. Look, h is defined with a logarithm, and we have the same logarithms everywhere and all linear. So the constant will just cancel. So no. The theory of heights is made with the natural logarithm, so base e. All the official theory of heights is done with ln, not with log in base 2. But it's the same. Eventually it's the same.
Okay, thank you very much, Teresa.